Hi everyone, Mr. Eric Kwa here, founder of Mr. Khemistry. Hope you're enjoying the videos that I've made for you specially. Remember to tap that like button and to click subscribe and to share with your friends if you found any of these videos useful or interesting. I look forward to seeing you around. Let's get started with today's topic. Alright, so this question is about transition metals, their property, and how they basically have formed colored compounds. So this is a part of the A-level syllabus, but the question has been adapted as a form of a database question for a secondary school prelim question. So basically, if you read through, right, you will realize that, hey, okay, so they basically tell you that that their valence electrons are the 4s and the 3d, 4s and the 3d, right? So they show you the way that you can actually write down. Next up, they show you all the electronic configuration, save for some. Okay, they also share with you that transition metal can have variable oxidation state due to the loss of 4s and 3d electrons. Okay, so titanium, which has two 4s and two 3d, can lose all four to give you +1 all the way to +4 oxidation state. Okay, then basically how do they form colored compounds? This data question is just sharing that, okay, when you actually excite a d orbital electron to go up to a higher energy level, it actually absorbs energy from a certain wavelength. And then when you absorb this energy, right, question goes on to say that the color that you observe by our eyes is the complement of the color absorbed. So they show you this color wheel, right, showing all the different colors and the wavelengths. Okay, one example is that copper, why do they appear blue? Their compounds, okay, because they absorb wavelength around 615, right, and then they reflect the wavelength about 470 nanometers, and that is actually blue color, which is the color that is observed by us. Okay, so that is all for the intro. Okay, so the first part they ask you, right? Okay, with reference to table 7.1, write down the electronic configuration of iron and cobalt. So iron and cobalt, basically you have them here, iron and also cobalt. Okay, so you have their proton number. You notice that basically they are just like 1 and 2 above the manganese. Okay, so all you need to do is just add on 1 electron and 2 electron to the 3d orbital, because they say that it can hold up to 10, right? Okay, it can hold a maximum of 10 electrons. Okay, you see that here. Right, so if we move down back to our question, yep, that is what we're going to write. Okay, this AR with a square bracket, right, basically is just the electronic configuration for argon. It saves you the trouble of writing the first 18 electrons. Okay, so save you the trouble of writing this electronic configuration of the first 18 electrons. Okay, and then state all the possible oxidation state that vanadium can have. So vanadium, if you look at the table, right, vanadium has a grand total of 4 s2 3d3, 5 electrons in total. Okay, so +1 all the way to +5. Is it possible for manganese to have oxidation state of +8? If you look at the table, right, manganese has a total of 7 electrons here, 7 electrons in the valence orbital. So maximum it can go is +7 and not +8. Okay, so they were saying that this sample solution Z, right, absorbs a wavelength of 680. What is the color of wavelength absorbed? Right, next part, they say it absorbs a wavelength of around 395. State the color observed. Okay, 680, you're going to talk about the wavelength absorbed. 395, you're going to talk about the color observed. Okay, so if you go to 680, 680 will be somewhere here. The color absorbed is red. And the next one is 395, it will be somewhere here. They want to get the color that's observed, so that will be green. Okay, so for the first answer, we have a red that is absorbed. Second answer, we have green that is observed. Okay, why is nickel able to form color compound when reacted with chlorine? Okay, so this part here, basically is the whole explanation that they have given to you right here. Okay, first is split into different energy levels, and then the electrons is excited, right? Higher energy d orbital, and then they will absorb energy from a certain wavelength. Okay, so the color observed is the complement of the color absorbed, right? So you can see that. Okay, so you're just going to transpose that to here. Okay, look at the last two parts. Zinc is a period tree with an electronic configuration of 4s2 3d10. So if you have a fully filled d orbital, right, you're not able to go through the excitation of these d orbital electrons. So basically, it's fully filled. You're not able to absorb and get promoted, absorb energy and get promoted to a higher energy orbital. Or another reason is the wavelength absorbed is not within the visible light spectrum. Okay, two possible reasons. Okay, last part, explain how the conversion shows that vanadium 5 oxide act as a catalyst. Okay, act as a catalyst because it is being used in the first part and is regenerated in the second equation. So let's take a look. Vanadium here being used up, and then it is again regenerated as a catalyst. Okay, so this is one example of a homogeneous catalyst. It itself is reacting and then it is regenerated at the end. Okay, briefly explain how a catalyst increases rate of reaction. Basically, this is under speed of reaction, right? Provides an alternative reaction pathway with lower activation energy. Okay, so that's all for this database question. Hope this helps.